the final value theorem in the Laplace transforms is another one of these consistency checks that relates the frequency function f of s to the time domain function f of t. In this case, to the limit as t approaches infinity of f of t, or the final value of t. This assumes that the final value of t is less than infinity, or in other words, that f of t is bounded. We'll see later on that this binding or constraining of f of t is equivalent to saying that the poles of f of s are all on the left-hand plane of the left-half side of the s-plane. So the final value theorem states that the limit as t approaches infinity of f of t is equal to the limit as s approaches 0 of f of s. Once again, we're going to start with the operational transform, the Laplace transform of the derivative operator, df dt, which by definition is equal to the integral from 0 minus to infinity, df dt e to the minus st dt. And as we have proved in the past, this transforms into the frequency domain as, or has the result of taking and multiplying s times f of s minus f of 0 minus. The proof progresses in this case by taking the limit of both sides as s approaches 0. So we have then the limit as s approaches 0 of this integral 0 minus to infinity df dt e to the minus st dt is, over on this side, equal to the limit as s approaches 0 of this thing here, s f of s minus f of 0 minus. Looking first at the left side, because the variable of integration is t, the variable s can be considered a constant. And in this case, we can go ahead and evaluate the limit as s approaches 0 before we worry about doing the integration. So we're going to have e to the 0 when we take the limit, and we're left with then the integral from 0 minus to infinity df dt e to the 0, which is just 1 dt. Now, to evaluate this, we're going to apply another limiting argument. We're going to say that this left-hand side can be thought of as the limit as t approaches infinity of the integral from 0 minus to t df. I'm going to use a variable of integration, a dummy variable for the integration here. So instead of t, we're going to call it y dy. Now, the integral of the derivative is just f of y evaluated from 0 minus to t, and we still have the limit as t approaches infinity. Evaluating this at both sides, we have then the limit as t approaches infinity of f of t minus f at 0 minus. Well, once again, this is a constant and is independent of the limiting argument. So we have then this is equal to the limit as t approaches infinity of f of t minus f at 0 minus. On the left-hand side, and we bring this on down over here, and we have then that this is equal to the limit as s approaches 0 of s f of s. And once again, because this is a constant, it's independent of the limiting argument, and so we just have minus f of 0 minus out here. Notice once again that we have the minus f of 0 minus on both sides. Those two terms add to 0, and we have what we started out to prove, which is that the limit as t approaches infinity of f of t, or the final value of t, is equal to the limit as s approaches 0 of s f of s. Let's do a quick example to demonstrate. let's use f of s is equal to 1 over s plus 1 over s plus 2, which we know now corresponds to an f of t equaling u of t plus e to the minus 2t u of t. Let's clean this left-hand side up just a little bit. We have then that this is equal to s plus 2 plus s, or 2s plus 2 in the numerator over the common denominator of s times s plus 2. Now, let's go ahead and write the limit as s approaches 0 of s f of s. Well, that's equal to the limit as s approaches 0. This term right here is f of s, so s times that would be s times 2s plus 2 over s times s plus 2. The s's cancel there. And now the evaluation of this limit is pretty straightforward. Since it's not going to infinity, s is going to 0. We have then, this term goes to 0, this s goes to 0. We're left with 2 over 2, which equals 1 on the left-hand side. Now, over here, when we take the limit as s approaches 0, it's got to equal the limit as t approaches infinity of this expression here. Or put it in brackets, u of t plus e to the minus 2t u of t. Now, the unit step function is bounded. It equals 1 for t, all t greater than 0. So the limit as t approaches infinity, the unit step function is just 1. On the other hand, this e to the minus 2t, as t approaches infinity, goes to 0. And we're left with this side here equaling 1. And sure enough, as advertised, the final value theorem says that the limit as s approaches 0 for this f of s, which we found to be 1, equals the limit as t approaches infinity of our corresponding f of t.